We're going to continue with equilibrium chemistry now. In the last session, we spoke about, or we visualized a kettle where each atom, each molecule of water broke free from the liquid, became a liquid to a gas. In the gas state, it hit the edge of the kettle, and it lost energy, it lost kinetic energy, its temperature dropped, it condensed to form water and went back into the liquid. The next step is to say, right, to conceptualize that what we've got is for each one that comes out, one goes back. So what we're saying is that as fast as we make up, so we break up, right? Now I'm going to use the Harbour process as our illustrative for this purposes. So the Harbour process essentially is this. So how do we start? Well, N2 gas plus H2 gas goes to double arrow here because it's reversible. It's an equilibrium reaction, it's reversible, to NH3 gas. That is an H2. Okay? So we're reacting nitrogen and hydrogen. We've seen this one a dozen times. Now what we're going to do is we're going to look at it. First of all, we always in chemistry start off, obviously if it's a theory question, we don't. But in everything else, we start off with a balanced chemical reaction because we need to know the mole ratios, okay? The recipe, how many cups of this to cups of that to get cups of that. That's the recipe we're after, and that's our mole ratio that we need. So what do? We say, all right, we need to balance it. That's the first step. So nitrogens, we need a 2 there, and we need a 3, and then we write down 1 plus 3 goes to 2. This is our mole ratio, correct? Our recipe, if you like. Okay. Previous years I've used the word recipe, but it's the mole ratio of the reactions that occur. Right. Now, that essentially is our Harbour process. Now, I'm just going to put in a few things here. This is the forward. Why? Because we said we are taking reactants and we are making products. So the forward reaction is making. That's just definition, right? We're making the products. The left is the reactants, the product is the... Obviously, we could switch this around and we could have ammonia on this side and we could be breaking it down. In that case, it would be reactant to product as well. So the reverse, the ammonia would be the reactant and the product would be that. That's we say left-hand side is our reactants, right-hand side is the products. Then we said the reverse reaction is that one. This is the reverse reaction, okay? Forward reaction and reverse reaction, okay? So that's the first thing we're going to do. I just put a double line down there. It's habit I do. The next thing we say delta H in this case is minus 92.4 kilojoules per mole. Okay, 92.4 kilojoules per mole. And what does that mean? It means that we've got an exothermic reaction. So let's just make a note here. Exothermic. And my apologies, I'm guilty at this stage. I am going to switch this off. I thought I had, so please excuse me. There we go. So now, what have we got now? Now we're saying that we've got an exothermic reaction. We've identified our products, our reactants. We've identified, as I said, that it's exo. We've got our forward and we've got our reverse reaction. So pretty much we are basically ready to go. The last thing we remember is that this is all in a closed system. Okay, a closed system. So we now put this together and we get it to get to equilibrium. All right. Now we're going to do the graphs a little bit later of this, but essentially what we've got is that the reaction is now reached equilibrium. So the rate of the forward is equal to the rate of the reverse. Remember in the beginning, it reacts fast. So you've got a big forward and a tiny little reverse arrow. But as time goes on, they equalize. Like the kettle, you get lots of steam initially, but very little drips down the side. Same with any of these reactions. So what we get, initially a fast reaction, it slows down, and the reverse reaction, small, it catches up. So that eventually we've got one hits the side, one goes in. Okay. Now, so the first thing we're going to say, now the equilibrium, okay, this equilibrium, it occurs at a 1 pressure. Okay. I'm going to use the standard that I've got here. Okay. I'm going to use, pressure, concentration, temperature. Let's go. Pressure, concentration, and 3 is temperature. Now, where does all this come from? Well, it comes from the factors that affect the rate of a reaction, doesn't it? Okay. The catalyst we're going to get to as well. Okay. Those are the things that we said, didn't we? The concentration affects it, the pressure affects it, and the temperature affects it. The Maxwell-Boltzmann curve. Okay. So where we are now is we're now saying, okay, we're going to examine our reaction has reached equilibrium. Here's our pot. So we put the nitrogen and the hydrogen in there, and we set the pressure and the temperature to a specific thing. We put in X number of moles of each, and we look and see what happens, how much nitrogen, how much ammonia we get at different pressure and temperature combinations. Yes, obviously, that's a lot of different combinations that we go through. And in most of these kind of experiments, you see a whole set of graphs, which gives you, at a certain temperature and pressure, you get a certain yield coming out of these, okay? Now, let's just have a look, all right? How do we deal with this? All right. Now, first of all, remember that let's just deal with pressure. We're going to talk pressure first. Okay? We're talking pressure. Now, I'm going to rewrite the equation. I'm going to say N2 gas plus H2 gas going to, there's my thing, NH3 gas. They're all in the same state here. Okay. So I say, okay, cool. Then I balance it, and that's going to be a 2. That's going to be 3. I write this down. 1 plus 3 goes to 2 moles, and there we go. Now I'm ready to rock and roll. Here we go. Now they tell me we're going to change the pressure. We are going to change the pressure. And we need to be able to say what happens. We need to be able to predict what happens. Now, in this case, we need to revert to, and you have to know it, it is called Le Chateliers Principle. You need to know how to state it, all right? And whichever version you get given thereof, you need to be able to go da-da-da-da-da and write it down. But if we unpack it, what does it actually say? It says something very similar, in my view, to Newton's third law, that if I push this, it pushes back. To every action, there's an equal but opposite reaction. So what Le Chateliers' principle said is I am now at equilibrium. So every molecule popping off into steam is replaced by a molecule coming in into water. Now I change this state. What is going to happen if I change the pressure? Firstly, we might need to remember that pressure and volume are related, right? Step one, okay, sorry, let's just go back to Le Chateliers' principle before we tackle the mechanics. Le Chateliers' principle is stating that. So what you have to do is we are going to identify the source of the disturbance. In this case, we are changing pressure. Okay. Then we say, right, the reaction will move to reduce reduce the change made to it. Which means if I increase pressure, it wants to move to reduce the pressure. Okay. You can see the similarities why I did it with Newton's law. But what are we saying? We're saying that, therefore, if I increase the pressure, the reaction is going to try to reduce the pressure. So the questions that we are going to be asked involve the forward and the reverse. Okay, I'm writing here delta H is equal to minus 92.4 kilojoules per mole. Now, under those circumstances, what happens? How do we do it? Step one is you work out the mole ratio. Then you check, are they all gases here? Okay. Because pressure only affects the gas portion. It doesn't affect solids or liquids. All right? Pressure, remember, no effect on solids or liquids for this purpose. Obviously, if you increase the pressure on a liquid, the pressure is increased, goes somewhere. So we say it's not affecting our relationship here. So the first thing I do is I write down and I identify the high pressure side. Now, before we get to that, remember pressure is proportional to volume. Okay? They are related. Let's go back and look at these things here. If I increase the pressure, okay, that's why I took the proportionality out. Okay? If I increase pressure, that means my volume is decreased. Let's think about it. Here's a box. Now you've heard the term gas syringe. It's a tube this side with a syringe that side, and we seal it. So if I now slide in, or if I push this top in, I am making the volume smaller and the pressure is going to go up. Remember that from physics? Similarly, if the pressure goes down, the volume goes up. As I move the syringe out, the volume goes up, it reduces the pressure inside. So pressure and volume are related, okay? And essentially, they could say to you, change the pressure or reduce volume, which means you'd have to work out if it's an increase or a decrease from delta V, okay? So pressure is inversely proportional to the volume. Now, we then say to ourselves, step one is write that down. So for pressure, you also need to remember PV is equal to nRT. PV equals nRT, okay? What does that mean? Well, PV equals nRT. N here is number of moles. Okay? R is the molar gas constant. Okay? T is equal to temperature in degrees Kelvin, correct? Pressure and volume is there. Now, so therefore, I can then say that my pressure is proportional to the number of moles. Obviously, it's proportional to the number of moles because if I think about it, if I put one molecule in here, one atom, one molecule of nitrogen in there, okay, it's going to bang around, but it's not really going to exert much pressure because it is too few. So the more I put in there, the more the pressure increases. It's like blowing up a balloon, right? As I'm blowing up the balloon, so the pressure increases, blowing up a tire as well. So the pressure is proportional to N, the number of moles of the gas, which therefore means, it means that on my equation over here, I'm just going to go back up to my equation. I now look and I say, okie dokie, this has got 4 moles of gas. This has got 2 moles of gas. Remember that recipe, the 1 plus 3 going to 2 is sacrosanct. Okay? That's exactly what it will always stay. All right? It can't react any other way because you can't have bits and pieces of things reacting. Now, that means that the one side of this is a high pressure side. And this is the low pressure. That's the low pressure side. Which means that our P and N, we can now use it because on the high pressure side, Okay, I will rewrite it so that we can use it again. We've got N2 gas plus 3H2 gas going to, in equilibrium, 2NH3 gas, delta H less than 0. We don't really need the number. And it's 1 plus 3 going to 2. And I said we add them together. So we say there's 4 moles here and 2 moles there. So this is high and this is low. Now, let's increase the pressure then, shall we? Okay. What did we say if we increase the pressure? Okay. Okay, blank. So we increase pressure, which means we decrease volume. If we do that, what happens? Well, what happens here is we increase the pressure, we decrease volume. Therefore, according to Le Chatelier, you have altered one of the states of equilibrium. Therefore, the reaction will proceed in the direction to reduce the change that you made. So if I've increased pressure, P has gone up. So what's it going to do? The reaction will favor the forward. Okay, this is just how we put it. It favors the forward, which means it makes product. Okay, why? So as to reduce pressure. Okay, so it favors, because what's it saying? It said, you've made me high pressure. I am going to go to the low pressure because I don't want the pressure on me. Okay, pretty human reaction, isn't it? The pressure's on us, we try and get the pressure off. So the same thing in a chemical reaction. As I push the pressure up, it seeks to reduce the pressure, so it will make more product. Okay, it favors the forward reaction. It favors the forward reaction. Well, if I reduce pressure, okay, increase pressure, reduce pressure, okay, all right, increase pressure, decrease the volume, that is increase the volume. Remember? Please know these two here as part of this. Okay, I'm reducing the pressure, which means the volume gets bigger. Okay, I'm making it a bigger space that the gas is in. So what am I going to do? According to Le Chatelier, I have affected one of the constraints or one of the things affecting a reaction. I'm therefore going to change it. What am I going to do? The reaction, this change will favor the reverse reaction. Okay? In other words, so as to increase the pressure. Pretty obvious. In other words, it makes reactant. Therefore, we have less product. All right? We have less product, which means the product concentration will drop. The product moles will drop. Okay? In other words, everything will be changed. But once you've identified this, the rest falls into place quite straightforwardly. Now, it's seeking to remove the disturbance that we have introduced. All right? Same as a human, we try and remove the pressure on us. Right? What about, for example, this one? Here's another example. Okay. We have H2 gas plus I2 gas going to, in equilibrium, H2HI gas. Hydrogen iodide, the manufacture of it. Now what? Well, what do? We balance. There it's balanced, and I put down 1. Let me just change my color. It's just doing the saving. Okay, let me just change my color here. Okay, I've got 1 plus 1, and on this side I've got 2. So 2 moles and 2 moles. There's no pressure differential between these. Therefore, the pressure change won't affect the reaction, will it? So if I increase pressure or decrease pressure, pressure doesn't affect it. It's not pressure sensitive, right? The rate of reaction stays the same, right? Now, what about we now take a different one and we say, oh, we go and we change concentrations, right? Righty-ho, let's move you up. Now what about concentration? We change a concentration. Let's go back to our standard into blah. Into gas plus H2 gas going to NH3 gas. And yes, we have a 2 and we have a 3 and we go 1 plus 3 going to 2. Okay, now concentration change. Well, what does it mean if we change concentration? It means we either add more stuff or reduce stuff. All right? So we can now say I can add more reactant, I can add more product, I can take away product, I can take away reactants, okay? Why do we need to do this? Because we want to control chemical reactions. It's critical that we control chemical reactions from a very simple perspective. You're working with hydrogen here. Hydrogen, highly flammable and liable to go up with a very large bang and cause a significant amount of damage. Therefore, it's a very dangerous gas. We therefore need to make sure that we can control reactions involving hydrogen. You do not want it to start going to a situation where, for example, the pressures start increasing too much. So we need to control it, and this is an element of control, right? Because we could reduce the hydrogen out of it, all right? Or do something else to use up the hydrogen that's in there. But in this case, concentration. Let's just stop and think. What does the word product mean? Product means we're making something. Why do we make it? We make it because we're going to use it. Okay, that's a fair point. If we're going to use it, it means that we don't want it in the pot. I don't want it in here. I want it in my canister, in my truck, into a factory, don't I? So what do? Well, on my side over here of my tank, of my pot, I put a little tap. And what do? I tap off the ammonia. So here's my little reaction vessel, let's call it. And in over here comes my N2, in over here comes my H2, and out over here comes my NH3 of my vessel. So now, I want NH3. My objective is to make it. It's a product that I use in detergents, in fertilizers, etc., etc. Therefore, I now, when it reaches a certain point, I come along and I open this tap and I remove NH3 gas. Therefore, the concentration is moles per decimeter cubed. What did I do? I took away moles. I took away moles, didn't I? By taking away moles, I have reduced the concentration. I have taken product away. Therefore, Le Chatelier says, you have affected my equilibrium. Huh? You've taken it away. What do I need to do? The reaction will thus produce more product. The reaction will tend to want to go back to equilibrium. So therefore, by removing product, the reaction will favor forward, okay, to produce more product. Correct? It will try and fill the gap. So as long as there's enough nitrogen and hydrogen in that tank over there, it will keep going. Okay? So as I keep removing it, so it's using up what's left. Remember, when it's a balance at equilibrium, the nitrogens and the hydrogens are changing to ammonia at the same rate that the ammonia is breaking. We're making and we're breaking. Every one goes another one that way, right? Now, in the ratio 1:3:2, obviously. Now, therefore, what I've got here is I've got a change. I've taken it away. The reaction says, hold on, you've changed the concentration, you've reduced it, therefore I need to get it back to where it was. So by reducing product like this, reducing concentration of product, Le Chatelier favors the forward make product. In other words, increase it again. On the same tack, well, what happens if I increase a reactant? Okay, Le Chatelier says it'll try and remove it. So therefore, I'm going to remove the increase by using it up, i.e. make more product. That's straightforward. Let us examine, therefore, what happens if we change a reactant into gas plus 3H2 gas going to 2NH3. All right? What happens if I reduce a reactant? Le Chatelier says we are at equilibrium, right? Delta H less than 0. We are at equilibrium now. Now I take away, let's say I remove some hydrogen. Okay. What does Le Chatelier say? It says I need to make hydrogen. Therefore, it will favor the reverse. Okay? It will reduce the product and make a reactant. It's always trying to keep this balance, isn't it? That's what it's after. It's trying to keep the balance. Okay? So, on the concentration, the last part of the concentration here is, let's just have a look. If we add a solid, okay, please note, if we add a solid reactant, okay, or a pure liquid, okay, reactant, all right, it doesn't change the equilibrium. Okay, just a little note. We're going to get to those in a bit. Okay, so that's the change of pressure and the change of concentration. I'm going to do some examples involving ones that do color changes and which way is it going to move. You'll see them in most textbooks. There's some classic ones. But essentially, just go back to the basics. The same applies when we get to the graphs. Go back to the basics. Have a look at which way the Chatelier says it's going to go. And then from there say, well, if it's going that way, I'm going to be using this and making that. Or I'm going to be removing product and making reactant. It's the safest, easiest way to go. There's no like, oh, if I do that, that's going to happen. Okay? Obviously because of pressure. The next one we're going to look at is going to be temperature. I'll see you on the temperature one. There's a recipe to follow for temperature as well. Cheers.